All right then. So, hello everyone. My name is Rączkowski, and I work as a senior machine learning research engineer at Allegro Machine Learning Research. And today I would like to talk to you about some work that we did recently regarding uncertainty estimation in BERT-based named entity recognition. So let's start quickly with an agenda. I'll start by describing what is the problem of named entity recognition and how we deal with this in Allegro. Then I will talk about uncertainty estimation, specifically about why do we need such a thing as uncertainty estimation, about Bayesian neural networks, and then about variational dropout. And then I will show some results of our experiments. And I will finish with some conclusions. So, as I said, let's start with the problem of named entity recognition in Allegro. So, as like I'm sure most of you are aware, and for those who are not, I will explain. So, Allegro is an online marketplace platform where registered sellers can basically list any product for sale. And these products can fall into any number of product categories. And they are parameterized by a set of like structured parameters, like you can see here. And also they are described by like a free text product description. So with named entity recognition, we are interested in actually both of these parts. So we take this free text description, and we might have a case where in some product categories or even for like specific products, we are missing some of these structured parameters. So the idea is that the sellers often like put these parameter informations into the text, not into the parameters themselves. So we want to basically like analyze these product descriptions and extract parameter values from them, and then fill in the missing values in these structured parameters. So you can see an example here where we have some product description, and we have these named entities. So these are basically our parameters that we want to fill in. And we can see that we can, for example, extract memory size, model name, and some catalog number. So as I said, then we can use these extracted values to fill in missing product parameters. And we do this basically to improve the quality of our product catalog. And down the line, this like enables our clients to better filter and find the products that we have in our offer, in our service. So now let's answer how do we achieve this. So we basically, in this named entity recognition system, we have a sequence tagging. We have a sequence classifier where, for example, for a sequence such as this, we can like split it into tokens. And here, for the sake of simplicity, we assume that these tokens are whole words. So we input such a sequence into a classification model, and then this model classifies each token into, in our case, one of three types of labels. So the first one is the O label. So this is out of entity. This is basically like a token that doesn't correspond to any entity. Then we have B entity, which stands for beginning of entity. And then we also have I entity. So this is in the cases where we have an entity comprised of multiple words. And each token that is subsequent to the first one is then classified with this I entity token. So Now you might be interested in this middle part. So when it comes to this classification model, we first of all pre-trained our own BERT language model. So we took, as you can see here, around 35 million product descriptions from our own data. And we pre-trained this masked language model with this data. And this basically gave us like a language model that knows the language of product descriptions. We then used this pre-trained encoder to like fine-tune this classification head. So this is just a linear classification head that is basically used to like solve this named entity recognition classification task. Okay, so now let's move on to uncertainty estimation. And let's first answer ourselves the question, why do we need it? So again, coming back to our named entity recognition model, we can like look at an example that is very easy. So we have some sequence, and then we can extract entities from this sequence, and most likely we'll get some very high probability scores for these entities. But what would happen if we were to get some ambiguous sequence, or even a sequence that lies completely out of distribution, like in terms of the data that we trained our model with? So in such cases, we might have some prediction, but when it comes to the probability score, it can be basically anything from 0 to 100%. And if our input example is truly out of distribution, this can even be very high. So we would have a very wrong prediction in such a case. So this means that we need some additional score, some additional uncertainty score that would tell us how certain our model is about its predictions. And like this is useful for out of distribution detection. So like you can see here in this example, but also for just identifying misclassified examples. So we can basically threshold our uncertainty instead of thresholding this just normal probability score. And also this can be useful for active learning. So we could use some uncertainty measure as an acquisition function in active learning. And we can, after testing some data set, we can evaluate the uncertainty and find which class is the most uncertain one, and then ask our annotator to give us more examples from this uncertain class. And then after adding these examples to our data set, we'll most likely get a better model. So now let's see how we can estimate uncertainty in our models. So one way, I think you can say, natural way of doing this is to utilize a Bayesian neural network. So let's explain what that is. So in a traditional neural network, or a standard neural network, when we train our model, we get a discrete set of weights. And then each time we input the same test example to our model, we get basically the same output. This is not the case for Bayesian neural networks, because when we train such a model, we don't get discrete weights, but instead we basically get a probability distribution for each of these weights. So then when we input a new example into such a network, we sample from these weight distributions. And this means that when we provide the same example multiple times, we can get different results. So with such a network, we then can look at the predictive distribution. And from that predictive distribution, we can evaluate uncertainty. So now let's look at that. So we have this predictive distribution given our training data set and some new input x prime. So, and this distribution can be marginalized in such a way where we have this integral. And what is a problem for us is this posterior distribution. So omega here is our model parameters. So for complicated models such as Bayesian neural networks, unfortunately, this posterior is intractable. So we need some way to approximate it. And one of these ways is to use variational inference. So those of you who participated in the talk today in the morning might remember some of this. So like this is basically the same principle. So we approximate this posterior with some variational distribution Q. And this Q is chosen in a way that we want to minimize the Kullback-Leibler divergence between this variational distribution and the true posterior. And this is basically equivalent to optimizing this variational lower bound, also known as ELBO, so evidence lower bound. And this basically gives us an expression such as this. So let's leave it for now. And let's see how we can like do this in a neural network like that we maybe don't think is necessarily Bayesian. So now let's look at a technique that is known as variational dropout. So in general, in neural networks, like our set of model parameters is like a set of weight matrices. L here is the number of network layers. And when we use a dropout during model training, we basically do something like this. So Ki here is the number of units in this layer I. And when we apply dropout, we either turn on or turn off the units in this layer. So this means we are basically like applying some mask to these units to turn them on or off. And we can think of this as basically sampling from the Bernoulli distribution. And when we look at the model training with dropouts as this, we basically like can say that this is our approximating Q distribution, which is parameterized by this MI matrix. So now when we go back to our variational lower bound, and we do Monte Carlo integration of this integral here, we can see that we get basically like this term is the model error, right? And here Wi hat are model parameters sampled from this variational distribution. So these are basically model parameters from a network with dropout enabled. And then when we also approximate this second term, for the details you can look in this paper from Gal and Garamani, we get a term like this. And this is basically just a regularized loss function. So with this, we see that training a neural network with dropout is equivalent to training a Bayesian neural network with variational inference. And now when we go back to our predictive distribution, we can basically do the same thing, but not during training, but during inference. So when we apply dropouts during inference, so at test time, we can also replace this posterior distribution with our approximating variational distribution. And then again, when we like use a Monte Carlo integration for this integral, we get something like this, which is basically just the model output probability averaged over so-called variational dropout calls. So this is basically a hyperparameter which we set for our inference process. and tells us like how many times we need to run inference for each test sample. And here again, these model parameters W hat are sampled from our variational distribution. So these are just model parameters with dropout enabled. All right, so now let's look how we can do this in a BERT-based model. So here you can see just the architecture of the transformer encoder from the original attention is all you need paper. And we can add dropout in multiple places, and this is done in the following way. So we add dropout after the encoding layer, and inside each attention head, after multi-head attention, and after the feed-forward layer. So this is basically just a simple operation that we can do. And with this, when we enable dropout both during training and testing, we basically get a Bayesian neural network from which we then can estimate our uncertainty. And in our experiments, we used dropout rate equal to 0.5. So we found that like this gave us best result. And we also set the number of variational dropout calls to 20 because we found that this gives the best trade-off between the time for inference and the results. So speaking of results, let's look at them. First, one more thing about uncertainty measures. We have this predictive distribution that we estimated with variational dropout. And then from that, we can calculate various uncertainty measures. And two of, let's say, most popular ones are the two that you can see here. So the first one is sampled maximum probability. And this is just like taking the maximum probability from each class over our variational dropout calls, and then subtracting this from 1. And the other measure is predictive entropy. So we calculate entropy for all classes, and then again average it over our variational dropout calls. So now moving on to the results. First of all, we found that just by introducing variational dropout, we were able to calibrate our NER model. So here in this plot, you can see a histogram that basically counts how many examples fall into given probability buckets. And when we don't have variational dropout enabled, you can see that the model is not very well calibrated because like most examples fall into these high probability buckets. And this is true for both correct and incorrect predictions. So if we were aiming for some level of precision, we would have to set a very high cutoff on probability to achieve that precision. And you can also see that in general, the most wrong predictions are also in this high probability region. So this is obviously not desirable for us. And then just by introducing variational dropout, you can see that the calibration becomes much better because most wrong predictions have low probability, and most correct predictions have high probability. So with something like that, we can then obviously identify misclassified examples. This is again the same plot as on the last slide. So this is basically 1 minus this USMP uncertainty measure, because we have probability here. But we can do the same thing with the entropy measure. So you can see here on the right that if we use this entropy measure as our uncertainty measure, we can also get like a very good separation between correct and wrong predictions, and like even a little bit better than for this standard sampled mean probability measure. And this is for like the whole entity level. We also evaluated this for like a single label level. So here on the x-axis is the ground truth label for the tokens that like were aggregated here. And here on the y-axis you can see just the uncertainty level. So this is this predictive entropy. And in all cases you can see that when we have wrong predictions, the median uncertainty is much higher than for correct predictions. And what's also expected, and it's good that we can see this on this plot, is that on average the uncertainty for these two labels, so when we do have our entities, is higher than the uncertainty for out of entity label. So this means that like the longer our entity, the more uncertain each subsequent token is. So for the beginning, we have like this level of uncertainty, and then for this I-entity label, we have much higher level of uncertainty. And again, on the whole entity level, this is still true. So the median uncertainty for wrong predictions is much higher than for correct predictions. Then we also were curious about out-of-distribution examples. So we performed an experiment where we trained our NER model with products from 3 different product departments. So from electronics, home and garden, and fashion. And then we also evaluated these models with 3 different test sets. So electronics, again, home and garden, and fashion. So these are indicated by these colors. And here on the x-axis, we have the train data set. And on the y-axis is, again, the uncertainty level. So in all cases, basically, the lowest median uncertainty is achieved when we test the model with the same department as it was trained with. And when we test the model with other departments, we get higher levels of uncertainty, and in some cases even much higher. So this shows that like clearly in the named entity recognition task, by using uncertainty, we can like distinguish out of distribution examples from in distribution examples. So that's basically it. So we showed that named entity recognition is an important problem in the e-commerce domain for an online shop such as Allegro. Then we also showed that variational dropout enables uncertainty estimation in neural networks, and that it can be easily enabled in a BERT-based model simply by adding dropout to the model. We showed that this technique improves model calibration in named entity recognition, and also that it allows for misclassification detection and out-of-distribution detection in this task. So now to quickly also give you some information about the team. So Allegro machine learning research deals with many different problems that we have in our service, and you can visit our dedicated website to learn more about us. And then specifically, our team is responsible for building models dealing with product data. And here you can see a photo from our recent trip to Babia Góra. And I can tell you with a huge amount of certainty that at this point we were very uncertain about our life choices. So yeah, that's it. Thank you for your attention. And do you have any questions?